Hello and welcome to our MedInfo 21 poster exploring molecular mechanisms within biomedical literature. This work is authored by Mrs. Nicole Glendening, Mr. Christopher Hawthorne, Mrs. Stephanie Beck, and Dr. Guillermo Lopez Campos. This work was carried out at the Wellcome Watson Institute for Experimental Medicine at Queen's University Belfast in the UK. We would like to start with a brief introduction and a rationale for our work that we are presenting today. Biomedical text mining allows deciphering important information and concepts that are hidden in large amounts of biomedical scientific literature. There are numerous examples of high-quality tools, such as PubData, that can be used for these purposes. We previously developed a biomarker analysis approach using PubData to identify similar and different molecular mechanisms based on gene annotations across different conditions. This approach was limited in its scope because it didn't include chemicals nor metabolites, and it had some technical limitations related with the loading of large annotation files. In this work, we present a modified and updated version of this methodology on which we are implementing new data structures. We are updating the annotation sources, moving from PubData that was based on the use of abstracts to PubData Central that is based on the use of full text, and expands the analysis to chemicals and metabolites. We apply this update in the analysis of potential biomarkers for preeclampsia. The material and methods for this poster are related with two different layers. The first one is related with the updates in terms of the data sources and analytical approaches. So managing the new structure of the PubData Central for comparative analysis, and also the performance incorporating the data through an SQLite database with one table for each annotation type using an edited version of the R package PubDataDB. Then we carried out a performance analysis, comparing the performance of the using the R package profits for the assessment of the performance, and comparing the read speed of the SQLite database, which is 16.2 gigabytes, against the annotation flat file that is slightly bigger, but it's still 16.6 gigabytes into R. We then carried out the preeclampsia analysis just to test the biomedical application of the new methodology, expanding the analysis to full text and the metabolites. And for this purpose, we analyze and we retrieve applying text mining annotations for genes and metabolites derived from the preeclampsia literature in PubMed. We carried out a pathway enrichment using Reactome as database of interest, and we combined the analysis of metabolites and genes to decipher the potential influence of preeclampsia of these elements using a Fisher's exact test with a Bonferroni adjusted p-value of 0.05. The results show that there is a significant change in the resources that are used between the new version, the update version, and the previous one. When we use just the chemical to PubData in the old version of our script that was before the update to the new PubData Central dataset, the system used approximately 21 gigabytes of RAM memory for this chemical to PubData. Using the bioconcepts to PubData dataset, this RAM consumption goes up to almost 29 gigabytes, whereas with the new version of the script and using the SQLite, it stands at 963, almost 964 megabytes, which is a significant reduction in the use of RAM memory, and makes it more accessible for its use in normal computers with smaller amounts of RAM. In terms of the time for the analysis, we can identify as well that there is a significant reduction from the use of the new version using the SQLite annotation, even when we are using a much larger data set than it was used before. So this is a very important and significant improvement over the previous version. In terms of the analysis, we were able to identify 893 metabolites and chemicals that were cited in the preeclampsia, in the literature related with preeclampsia, and we identify 1,271 genes. From a pathway perspective, we can see on the Venn diagram on the right that the combined analysis where we mix and merge together metabolites and genes for the analysis in Reactome is the one that is giving us the higher results. And it takes almost all the pathways that we were able to identify. The gene analysis on its own was able to identify 293 different reactome pathways. The analysis of metabolites on their own identify only 34 pathways, but when we went to the combined analysis, this went up to the almost 1,100 different pathways, and we were checking those with some experts in the domain, and those made sense. So as a conclusion, the new updates have allow us now to incorporate the use of metabolites. We have implemented a new approach that is based on the retrieval and analysis of a combination of chemical and metabolites, and it provides a deeper insight into potential biological mechanisms. From a performance perspective, we have increased the performance of our system through time and resource consumption reduction, and the analysis of identified metabolites and genes has allowed us to highlight some mechanistic pathways that are underlying this condition. Thank you very much for your attention, and if you are interested in knowing more about this work, please do not hesitate contacting Dr. Guillermo Lopez Campos at g.lopezcampos@qub.ac.uk. Thank you very much.